This is an honor. Peter is a longtime friend. Everybody on this webinar knows who Peter is. He is the founder of RPG. It's become an iconic 3 letters in our industry, and has in the last few years dedicated his life to pure research. Longtime associate of WSDG, and now with the assistance of WSDG and other people, is director of research for Redi Acoustics, an organization that is completely and solely dedicated to research, tackling some advanced acoustic issues. Our first one is low frequency analysis, which clearly is the bane. It's the 500-pound gorilla in all of our designs, particularly small rooms. He's an iconic person in our field. And so with further ado, what is that ado thing? It's from Shakespeare, right? I think this ado business. Anyway, Peter, welcome. Start off by telling us where you are. I know you're on the East Coast, but I'm never quite, I think you're at home, right? Or Washington?
I am actually in my residential lab in the state of Maryland.
Okay, great. Well, welcome. And everybody fasten your seatbelts. If you thought Dirks was complicated, it's about to get even a little bit more. Please don't leave though. Don't leave. You got it, Peter.
Thank you, John. Well, greetings, everyone. Niro is the first wave-based non-cuboid iterative room optimizer, which we are introducing today. These images that you see here are actual pressure plots at 2 modal frequencies and can be thought of as the new acoustical Greek theater masks for comedy and tragedy. They illustrate the challenges an optimizer program faces to simultaneously find the best polygonal geometry and positions of speakers and listeners so that they avoid the blue low pressure areas and the high pressure red areas to obtain the flattest response at all modal frequencies. Earlier dimensional ratio approaches to optimize the modal response were based on modal spacing, like the Bolt amoeba and the criteria by Bonello and Loudon, which Dirk mentioned. These methods are based on the well-known wave equation. So despite the amount of attention this simple approach has been given, sorry to say, it is not sufficient for the design of critical listening rooms because it does not consider the location of speakers and listeners. Optimal dimensional ratios are a myth because in real cuboid or non-cuboid rooms, the degree of excitation depends on the positions of the loudspeakers, but the degree of audibility depends on the position of the listeners. RPG's Room Sizer program went beyond modal spacing and iteratively optimized dimensional ratios by minimizing the standard deviation of the modal response. However, the speaker and listener were required to be in opposite diagonal corners. For cuboid rooms, this situation of loudspeaker and listener placement was properly handled in RPG's Room Optimizer. However, it still did not simultaneously address the room geometry and the positions of speakers and listeners in a polygonal room, hence the need for a wave-based, non-cuboid, iterative room optimizer, which we call Niro. Niro completes the research that Professor Trevor Cox and I started over 2 decades ago and provides an iterative optimization program for non-cuboid rooms with the addition of low-frequency dampers to optimize the frequency response and temporal decay. This is quite a bit more challenging because we now must account for the actual complex impedance of the room's boundaries and contents. We have to optimize the coordinates of all intersection vertices of the boundary, as well as the coordinates for the speakers and listeners, instead of just determining the optimal length, width, and height dimensional ratios. We have to determine the modal and SBIR responses using a time-intensive, discretized boundary element method with hundreds of boundary elements and high-frequency resolution, instead of the rapid image model. We have to use a genetic algorithm to iterate hundreds of times due to the large number of variables and possible solutions. We have to insert pressure absorbers into the mesh with known complex impedances, to further damp any remaining modes that exceed a specified threshold. This is a shout out to our visitors who are speaking German. What we're seeing here are the actual modes in a cuboid room. Now to speak about the SBIR, which Dirk alluded to, the resulting interference is called the SBIR and presents itself as a dip in the low frequency response. We have a pause for a commercial. But wait, you buy one speaker and you get 4 virtual speakers free. Okay.
And Peter, I am going to interrupt because 3 different people have asked over the same question about how do we deal with reflections behind the loudspeaker. This could be a perfect time to talk about it.
Yes, that is handled in the next here. In Niro, we deal with this automatically and estimate the SBIR at the listening position through the windowing and Fourier transform of the impulse response. So the rear reflections, well, all of the nearby reflections occur within about 50 or 60 milliseconds. So by windowing the impulse response and taking the Fourier transform, we can deal with all of the SBIR simultaneously with the room modes, which I'll be talking about in a minute, if that answers the question, John.
Good.
Now, the frequency response is only a part of the equation to achieve a good bass response. Our brain integrates the continuous sonic input, meaning that we perceive the temporal decay, which we need to damp for a tight bass response. A proper decay of the room modes is fundamental for a good perception of sonic quality in the low end. Through the application of precisely designed dampers, the frequency response and the decay of the room modes can be controlled without introducing unwanted dips at the wrong frequencies. In small critical listening rooms, the design goal is to provide absorption at specific modal frequencies with a specified bandwidth and maximum absorption to control the modal resonances. Large broadband treatments like so-called bass traps are inefficient and not precise enough. We call these new pressure absorbers acoustical parametric equalizers, or APEQs, analogous to the electronic parametric equalizers. Their placement is also key. Otherwise, we might end up absorbing more frequencies than intended. In the first example shown, the bandwidths of 2 APEQs are too wide, leading to an unintended dip at 55 Hertz. In the second example, the design frequency is incorrect, leading to a dip at 53 Hertz instead of where it is really needed. Breaking news. This new non-cuboid iterative room optimizer program is both a design and a diagnostic tool, which currently contains 3 modules. The geometry module iteratively optimizes the shape of a polygonal room and the locations of speakers and listeners by minimizing the weighted sum of the modal response and the SBIR, in answer to that question, John, using a BEM and a genetic algorithm, which we will explain next. The damper module applies parametric pressure absorbers tuned to frequencies that exceed a threshold in the modal response from a library of APEQs, calculated with the transfer matrix method. The specular reflection module calculates the first and second order reflections in a similar way that Dirk described, arriving at the listening position and the rear wall diffuser to optimize the creation of a reflection-free zone and a diffuse immersive environment, which we'll talk about. The boundary element method is a general wave-based approach which can simulate scattering from any shaped object or behavior within this object by solving the wave equation at any point in the domain. It follows a multi-step process in which first we mesh the shape into small enough elements to represent the wavelength of the highest frequency of interest, generally 1/6 or 1/8 of that wavelength. Then we have to solve hundreds of simultaneous equations, the Helmholtz-Kirchhoff equations, to determine the pressure on each mesh element, as you see here. These different colors represent the mesh element pressures. Then we plug those values back into the HK equation, and for a given incident pressure, we solve for the pressures at any point in the room using a 3D Green's function as the source. The initial vertices that you see here are combined into planes, which are automatically meshed in a program called Gmesh, which is shown at the right. The geometry module. This module is designed to find the best combination of room geometry, source and listener positions possible, given each room's flexibility. In order to do that, an allowable range for all of the X, Y, and Z coordinates must be defined for the following. This range dictates how much the room boundaries can move and in which directions. This listening range specifies the area in which the listener can vary. The source range specifies the volume within which the sources can vary. This calculation utilizes the complex impedance of the room boundaries in order to account for phase changes, which are not accounted for in the image model. It also relies on a genetic algorithm to perform the room optimization process. Okay, this is kind of the heart of the program.
Peter, I think it's important at this moment, and I know we promised to not interrupt that because I'm seeing at least one question. Even if you have a room that can't change, and many people have rooms that you can't change the dimensions. In other words, when we're designing, we can change a lot of dimensions, okay?
Right.
But if you have a room that's XYZ, it still doesn't mean you don't have geometry options. You have geometric options in speaker placement and listener placement. Okay?
That's correct.
And this is critical. This is super critical, and it could be the difference between successful low frequency response and non-successful.
Well, that is really true, John, and that's why I say optical room dimensions are a myth, because you can have a perfect dimensional ratio, but if your speakers and listeners are in the wrong place,
yeah,
you're either sitting in a black hole or you're sitting on the top of a mine. So, excuse me. And then, if the geometry is fixed, you can then vary the listener and speaker positions, but you can also add low frequency absorbers. Which we do all the time when the geometry is fixed, and we'll talk about that in a minute. But that is a really good point, because you know many rooms are just fixed, and so the challenge, if you think back to those pressure plots that we started with, the challenge is working your way through that minefield to stay away from the black holes and stay away from the mines, and the only way you can do that is to use a search engine. And the search engine that we have chosen is called the genetic algorithm. And the genetic algorithm essentially mimics the process of evolution, you know, the famed survival of the fittest over several generations. And so I'm going to be alluding to this graphic here as I describe the various steps in the genetic algorithm. So we begin with the initialization. This first step is used to create an initial population of n randomly generated candidates whose pseudochromosome consists of genes, which are the X, Y, and Z coordinates of the speakers, the listeners, and the room's vertices, as you see here. During each evolution, every evolutionary iteration of ROGA, the BEM is used to evaluate the performance metric. So you have all of these evaluation stages here. Then you get into the selection process. A biased roulette wheel is used to select the candidates for the next step. The wheel is spun n times to maintain the initial number of candidates. The best candidates are automatically sent to the next step, even if not noticed. And candidates that have a higher fitness value have a larger portion on the wheel. So now we get to the fun part. Two random promiscuous strangers meet over drinks in a bar that should really be closed during the pandemic. They have sex and they breed, producing an offspring whose genes are determined via a coin toss. We get then to the mutation stage. Each candidate, old or new, has a chance to have one of its genes changed to a new random one, which will keep the population diverse and increase the gene pool. We don't want to have too much inbreeding, or we won't get to the appropriate answer. It also is used to remove duplicate candidates before moving to the next generation. Now, at this point, if we have met the criteria, we can stop and move on to the next process in the optimization. If we don't meet the criteria, we just go to the next generation, and we can stop it if we reach a limited, a specified number of generations as well. Now, the fitness metrics that we use corresponds to the weighted sum of the standard deviation and the modal response and the SBIR. To just bring back in mind what Dirk was talking about. We're doing both of them simultaneously, and we're weighting them depending upon which of them has the more relevance in that particular room. Now, it also contains a very important penalty factor to reduce the dips in the frequency response, because these dips cannot be later equalized when they exceed a threshold. If you have them, you're going to be stuck with them, which is why you have to go through all of these iterations of the genetic algorithm to avoid those black holes. Now, in critical listening spaces, the goal is to generally achieve the flattest frequency response possible. However, in audiophile listening rooms or home theaters, metrics like the equal loudness contour can also be used to change the total balance of the response. And what you're seeing here is an actual optimization in progress. Every time you see the graph changes, we are going through another iteration in the genetic algorithm. And so in the upper left, you see the worst, the best, and the current spectra. And it's a combination of the modal response and the SBIR. To the right, you see the progress. In other words, we're plotting the fitness versus the generation. And you may have just noticed that the fitness value decreased from the initial position to the next lowest one to the next lowest one. Eventually, we will arrive at the fitness metric that we would like to have. In the lower left, you see the room. Well, it has just stopped, but in the lower left, you saw the room varying, where you see the geometry is changing and the speakers and the listener are all simultaneously moving. And then on the right, you see the same situation in the section. And this continues until we get a solution that we like. Now we have a damper module. And this addresses the question that John raised. You know, if we have a room, and let's say the speaker and the listeners are even fixed, the only recourse we have is to use the damper module. And then by using the transfer matrix models, which I'm sorry, I don't have time to describe, we can predict the acoustic impedance of multi-layered acoustic treatments, such as membranes, Helmholtz resonators, and also porous absorbers, which are only applicable in the higher frequencies. Now, this enables the creation of fine-tuned acoustic absorbers to treat the resonant frequencies of each different room with precision. From the estimated impedance, we can calculate the absorption coefficient and the acoustic admittance that will allow for precise calculation in the boundary element model. The resonant frequency is first measured with an accelerometer that you see in the lower right of your screen to determine that we have the appropriate resonant frequency. The final impedance is verified in RPG's 7-ton impedance tube to ensure accuracy. Here you see the tube with the lid open. It's a 7-ton, 24-foot long impedance tube. Here you see the complex impedance, the real and the imaginary part. Imaginary part crosses zero at the resonance. Here you see the reciprocal, which is called the admittance. And then from the impedance, you can calculate the absorption coefficient. Now, the amount of absorption needed for each resonance is defined by evaluating the Q factor of each mode and the waterfall plots to ensure the right amount of treatment is added. Specular reflection module, early reflections. By using the image source model that Dirk described, we can trace the origin of the important first and second order specular reflections. Now we're moving above the Schroeder or transition frequency because we have to treat those reflections as well. What you're seeing are the first order reflections here for simplicity. This next graph shows these first and second order reflections which is obviously more complicated. Now, this will determine if a boundary needs to be reoriented or treated with broadband absorption. Because we have to control these reflections, it's crucial for proper imaging at the mixed position, essentially creating a reflection-free zone, which we introduced 3 decades ago, which is followed by the diffuse rear wall reflections that you see here. Now, the specular reflection module also addresses diffusion. By analyzing the direct sound that you see here, these are the speakers and this is the listener. By analyzing the direct sound and the first order rear sidewall and ceiling reflections. So here's a first order sidewall reflection. Here's a first order ceiling reflection. We can determine the size and precise placement of the diffuser to provide ambiance and envelopment, which is very important in a room, that it not be too dead, because you're introducing signal processing that has to be listened to in a real live room. Now, most DIY diffusers, unfortunately, or conventional QRDs, do not have a necessary diffusion coefficient above 0.5 from 400 hertz to 5,000 hertz. For more information, you can see the ISO standard listed here. We must also reduce periodicity, which means placing the same diffuser next to each other, which degrades performance. By utilizing modulation with an optimal binary sequence, and this is a presentation all in of itself. A further increase in bandwidth over that of each individual diffuser can be obtained by creating a diffractal, meaning embedding a diffuser within a diffuser, which we are using in several, specified in several rooms. So now, how do we evaluate how accurate these predictions are? We've created a Redi lab for testing. And it was created using the same boundary construction as is commonly found in control rooms or recording studios, which helps to verify the complex impedance values used for the room's boundaries. You know, these values are not listed in a table. You can't go to the back of a textbook and find the complex impedance values. And so it's really important that they have to be measured and they have to be evaluated in actual rooms, which is what this lab is important to helping us with. So as you can see, the agreement is really, really very good. Once again, a proof of the precision of the boundary element method. Here you see the room with the loudspeaker here in this corner and the microphone in this corner and the loudspeaker in this corner and the entry doors. You see the agreement is really, really good. This is the sub that was used with its roll off, and that's why we have this difference down in this low end. To further evaluate the precision or the accuracy, actually, we looked at a real, well, before I mention that, in order to evaluate the decay of the room modes, we also compared the reverberation time calculation from prediction and measurement. And as you can see, the fidelity of the method still holds down in the 31.5 hertz band. So then to move on to an actual real project. In order to further verify the accuracy of the program and improve the precision of the transfer matrix method, a real project was reverse engineered to serve as a benchmark. At this point, it cannot be assumed that all of the recommendations were fully implemented, so there are some unknowns. But nevertheless, the specified geometry, the speaker listener placement, positions rather, and the finishes were used in the model, and the predicted and measured frequency responses are shown below. You know, considering all of the unknowns, this agreement is really pretty excellent. And so with that, I will, with that, I will end my presentation and thank you all very much for listening.